Go! Alright, this is section 1.9, Pre-Calculus Instructional Video. So, today we're going to be talking about finding the inverse for a function, algebraically and graphically. We're going to be verifying if two functions are inverses or not by using the composition, and identify if a function is one-to-one or not, and how that affects whether or not it has an inverse function. So let's go ahead and get rolling here. So, just a little bit of an intro before we actually start talking about inverses and functions and all that stuff. Let's talk about what an inverse is. So, the word inverse more or less means like the opposite. So if I have like the number 5 and the number 1/5, these are what we call multiplicative inverses. Right, just dealing with some numbers here. This isn't, I'm setting up what we're going to learn about functions. Because these are multiplicative inverses, because if I multiply them, 5 times 1/5 equals 1, and 1 is what we call the multiplicative identity, which means 1 times anything just gives you that anything back. Like 1 times A is just A, right? If we take a number like 5 and let's say a number like -5, these are additive inverses. So if I take 5 plus -5, I get 0, right? And 0 is the additive identity, because like 0 plus A is just A. Like 0 plus anything is just what it is. So with like addition, every number except for 0 has a with multiplication, I pointed at multiplication. With multiplication, every number except 0 has a multiplicative inverse, where if you take that number, multiply it by its inverse, you get 1. 0 is special, because you can't divide by 0. Right? With addition, every number has its additive inverse. So if you add those two numbers, it would just be the positive and negative version of that number. If you add those two numbers, you get 0, which is the additive identity. So if we want to talk about the inverse of functions, we got to say what operation are we talking with respect to. And in this case, it's going to be the composition. So here, we want the inverse with respect to, so WRT stands for with respect to, composition. With respect to the composition of functions, where if I take two functions, f and g, and I compose them, I get the identity function, where the identity is with respect to composition. So, let's think, what function would be our identity function? Let's call it h of x. Well, I'm just going to tell you. Think about it though. H of x equals x, maybe I should make it I of x, make identity, doesn't matter, is the identity function because if I take any function f and compose it with h of x, so f of h of x, what I'm going to do is I'm going to take my f of x function, I'm going to replace all the x's with x's. And I'm just going to get f of x back. In other words, doing the composition with f of h of x, where h of x is the identity function, doesn't change the function. Just like 0 doesn't change addition, just like 1 doesn't change multiplication. So what we're looking for here is we're looking for functions where if I take the composition of the two functions, I just get x, or f of g of x equals x, right? Those being the same thing, right? And it's got to work both ways too. So let's look at, that's it. Two functions are inverses if and only if you take the composition f of g of x and you get x, and g of f of x gives you x, right? And this is just like what it means in the different notation. So if f and g are inverses, we don't write them as f and g anymore. We write them as f, function f, and f inverse. So we have f of x and f inverse of x. Where this little -1 is, it's not an exponent. It's not saying divide by f one time. It's not saying that. It is just a little notation saying that this is the inverse of that. And if it was g of x, you would have g little -1 of x to represent the inverse of g. Okay, so basically, inverse functions are functions that undo each other with respect to the composition. So everything that f does to x, f inverse does the opposite in the opposite order. So the inputs for f of x match the outputs of f inverse of x, which means whatever the domain of f is, that's your range for f inverse. And vice versa. And similarly, the outputs for f of x have to match up with the inputs for f inverse of x, because they're doing the opposite. Whatever f does, f inverse does the opposite of. So whatever your inputs are here, those are going to be your outputs there, because that's the opposite. Whatever your outputs are for f, those are your inputs for f inverse, because they're opposites. So here, the range for f is your domain for f inverse. So sometimes, if we get a function like, well, sometimes we'll get a function where if we take the inverse of it, the inverse itself is not a function, and you'll have to restrict the domain on the original so that when you take the inverse, you get a function. All right, let's go ahead and do some math here. I mean, this is all math, but let's do like an actual math example and, you know, put some numbers and variables and stuff in there. All right, let's go ahead and do this. Do this. Okie dokie. Let's say we have, and this is an example straight out of the book. So f of x equals 5 over x minus 2. G of x equals x minus 2 over 5. H of x equals 5 over x plus 2. All right. Well, what we're going to do is we want to find which pair of functions here, f and g, f and h and g, which pair are inverses of each other. So which of these, which are inverses? Okay, cool, we can do that, sure. How do we know if they're inverses? We know if they're inverses if we take the composition and the answer is x, right? That's what I just erased over here. So what I'm going to do is I'm going to say f of g of x. F of g of x. What I want you to do, right, remember that's how we write it, fog f of g of x. I like it better in this notation. The book uses this, so be familiar with this. They mean the same thing. Go ahead and find f of g of x. Go. Pause it and go. I meant pause it. Hopefully you unpause it, and we're back. So I'm going to take my f function, and I'm going to replace the x with g of x. So I'm going to get 5 over x minus 2 over 5 minus 2. So I replaced this x with g of x. All right, now I got to like simplify, right? So I got to say, well, This is over 5, so I gotta multiply this by 5 over 5 to make it 10 over 5. Now I'm gonna go 5 over x minus 12 over 5. Right? Yep. And then this is 5 divided by x minus 12 over 5, which gives me, just making sure I'm actually doing this correct. Pretty sure I am. Where am I? Sorry, just a sec. Divide, that's flip and multiply, so 5 times 5 over x minus 12, which gives me 25 over x minus 12. That's not equal to x. Doesn't work, that's not it. I think the book has a different problem than that. Or I goofed somewhere. I don't see where I goofed though. That's okay. Did I goof? If I did, please send me an email. I might have goofed in my algebra there. But I think it's okay. Yeah, all right, so now let's look at f of h of x. F of h of x. Right, this is f of h of x. So what we're gonna do here is I'm gonna go 5 over, instead of an x, I'm gonna put in h of x. So I'm gonna put in 5 over x plus 2, and then there's this minus 2. And I'm gonna simplify. Well, hey, check it out. Plus 2 minus 2, that's a 0. Yeah. So we get 5 over 5, oh, that's a 5, not an 8. 5 over x. That's 5 divided by 5 over x. That's 5 times x over 5. It's x. Hooray! Then we can check h of f of x as well. Go ahead and try that on your own. You should get x. And you will get x, which means f and h are inverse functions of each other. Okay. And then you can check the domain and range of the two if you wish to see that the domain of f is your range for x. Let's just see that. So, domain here, x cannot equal 2. Range here, we've got 5 over x, which makes this a, reciprocal function like this. That's our parent function, 1 over x. But it's been shifted up 2. So instead of x is not equal to, y is not equal to 0, y is not equal to 2 is our range. Works. The domain here, x can't equal 0. The range here, there's no shift up or down, so y cannot equal 0. So the domain and range swap, we're good. All right. So, a little bit more to write here. A little bit more notes, I guess. Notes, taking notes on a YouTube video, that's fun. So graphically, uh-oh, it's getting graphic, y'all. And this graphically means on a graph, not like cool graphics or, anything like that. On a graph, every point, a comma b, on a function f, on the function f, sorry, not is, occurs, or coincides with, occurs as a point b comma a on f inverse. So every point, a comma b, so x number, y number, on the function f, occurs as a point b comma a. So the swap of those two on the inverse function. And let's just see. Like, what if I take, in this case, f of f inverse of b. If I take that composition, right, I should get b. Is that going to be equal to b? Let's find out. Woo. Okay, well, first we go, well, what's f inverse of b? Well, f inverse has b comma a. So f inverse of b is a. And what's f of a? Well, it goes to b. Hooray! Same thing. If I go f inverse of f of a, the x number is a, well, f of a is b, right? Because a goes to b. F inverse of b is a. So it equals a. We're really happy, right? Cool. All right, so let's look at, let's say that the function f of x is more than like 2 points on it. Let's actually do like a little table example here. Let's table it for right now, not table it for later. So let's say we've got this x, y table. We got 0, 0. 4, 2, let's say we have 9, 3, and let's say we have 16, 4. And this, sorry, instead of x and y, this is x and this is f of x. What I want you to do on your paper that you're working on right now, I want you to find the table x, f inverse of x. What is that table going to look like? Go! Pause the video, go! We got some water left in here. Getting parched. Well, hopefully you unpaused, or you did it. What we're gonna do for this, oh, I didn't, that's okay. We're just gonna switch these. So 0, 0 stays 0, 0. Instead of 4, 2, we're gonna get 2, 4. Instead of 9, 3, we're gonna get 3, 9. Instead of 16, 4, we're gonna get 4, 16. We just swapped the x's and y's, right? Every a comma b is now a b comma a. 4, 2 is now a 2, 4. 9, 3 is now a 3, 9. If we're going from function to inverse or inverse to function, swap the x's and the y's. Cool. Now, and sorry, I should have had this in there. 1, 1. 1, 1. If I sketch this graph, sketch this one. 0, 0, 1, 1, 2, 3, 4, 4, 2, 7, 8, 9, 3. So we got this right here. And let's say we have, I should have done that in green, my bad. Green, this is the green graph. I'll just go over it in green. That's the green graph. That corresponds to this one. I didn't go all the way up to 16. That's okay. 5, 6, 7, 8, 9. So 0, 0, 1, 1, 2, 4, 3, 9. How does the green graph correspond to the black graph? Like, what do you notice? How could you go from this green one to this one? What physical move, transformation, could you do? Give you a moment to think about it. Think. It is a reflection in or over or across the line y equals x, which remember, like h of x equals x is our identity function. So if we reflect through that identity function, we get the inverse function. So like this point here, 4, 2, when I reflect in y equals x, that becomes 2, 4. All right. So we're going to do a little action with that. Let's say we have the graph. The graph of f of x equals x to the third minus 1. And let's say we have the graph of f of x equals x squared minus 1. These are two separate graphs. What I want you to do is pause the video and graph both of those. That's a little 1.6, 1.7 review, so go ahead and do that. And then when you unpause it, I'll be working on this. We're going to do it on separate grids. So here, there's a grid. There's a grid-ish. All right. What am I doing? There we go. Negative 1, 0, 1, 2, 3, 4, 5, 6, 7. Negative 1, 1, 2, 3, 4, 5, 6, 7, 8, negative 9. All right, so we got green here. 1, 2, negative 1, negative 2. More or less like that. That's what x to the third minus 1 looks like. And here, negative 1, 1, 1, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8. All right, this, we're going to have a vertex at 0, negative 1, 1, 0, negative 1, 0, 2, 3, negative 2, 3, 3, comma 8, negative 3, comma 8. We had a graph that looks like that. More or less like that. All right. So now what I want you to do is reflect each of those in or over the line y equals x and find the inverse graph for it. So go ahead and pause the video, do that. And to graph y equals x, what you do is you just go like negative 1, negative 1, negative 2, negative 2, 3, comma 3, that sort of thing. So you draw a diagonal. Draw a diagonal. And I'll switch colors. I'll do each inverse in purple, because that's another color I have. So here, this 0, negative 1 here is going to be negative 1, 0. It reflects over the other side. This 1, 0 is going to be 0, 1. This 2, comma 7 is now going to be 2, 3, 4, 5, 6, 7, comma 2. It's got to be a little higher up to be at 2. There we go. This point down here at negative 2, negative 9 is now going to be negative 9, negative 2. 2, 3, 4, 5, 6, 7, 8, 9, negative 2. And this point here, negative 1, negative 2 is now going to be negative 2, negative 1. We're going to push this down a little bit again. So we get a graph that looks like that. Yeah, there it is. So it kind of looks like that. It's this one, we go, whoop. It's like this part here flips over here, this part here flips over there. So everything that was going up is now going over, everything that's going down is going that way. All right, now let's do it with this one. So here, this negative 1, 0 is going to be a 0, negative 1. We're just changing the x's and y's. This 1, 0 is going to be a 0, 1. This negative 1, 0 is going to be a 0, negative 1. This negative 2, comma 3 is going to be a 1, 2, 3, negative 2. And this 2, comma 3 is now going to be a 3, comma 2. So I'm going to get a graph that looks like this. All right. What do you notice between those two purple graphs? Which of those purple graphs represents a function? It's this one, right? Is it that one? Why is this one a function and not that one? It's not a function because, this one's not a function because this graph, this sideways parabola, does not pass the vertical line test. In other words, like when x is 3 here, I have two outputs. right? And a function for each x is one and only one y. For each input, one and only one output. Each input has exactly one output. Here, this input has two outputs for the purple. Here, every vertical line I draw, one and only one output. This purple graph, the inverse of x to the third minus 1, is an inverse function. Here, this inverse graph is not an inverse function because it's not a function. Okay, cool. So how could we tell that without actually graphing it? Well, if I make this vertical line right here at x equals 3, what does this vertical line at x equals 3 on this inverse correspond to on the original function? A vertical line here, if I reflect a vertical line over y equals x, it becomes a horizontal line. And we now have the horizontal line test. It's like the vertical line test. The vertical line test tells us whether a relation is a function or not. If every single vertical line you could possibly draw meets the graph once and only once, then the relation is a function. If it ever hits two spots in the graph, not a function, because that means one input has more than one output. Now, the horizontal line test says if every horizontal line, which I'll draw over here, if every horizontal line hits the original graph once and only once, then that function has an inverse function, and we call that function a one-to-one function. 1 to 1. In other words, each x has one and only one y. Each y comes from one and only one x. That's what one-to-one means. Now, to fail the horizontal line test, that's when any horizontal line, and all it takes is one horizontal line, intersects the graph more than once. So for example, here, this horizontal line at y equals 3 intersects the graph at x equals -2 and x equals +2. And that corresponds to when I take the inverse, that's that vertical line test failure. So the horizontal line test says if every single horizontal line hits once and only once, then that function has an inverse function. If it fails the horizontal line test, if a function fails it, in other words, like this parabola, if a horizontal line hits the graph more than once, then the inverse of that is not a function. In order to make an inverse function, what we would have to do is restrict the domain and say, oh, let's just talk about that part. And maybe just go everything to the right of the vertex, something like that. Okay, cool, let's move on. That's the horizontal line test. Let's find some inverses algebraically. Let's do a little algebra. Yeah, cool, let's do it. And now I'm going to silently erase stuff. All right, we're going to do two problems. We're going to find the inverse of each function. We're going to start with f of x equals square root of 2x minus 3. We're going to do that one. And then we're also going to do, I'll let you write that down. We're also going to do this function. This is going to be a more interesting one. This, you'll definitely have to do this level of difficulty on the homework and on assessments. Yeah, for sure. The second one has some really good algebra in it. We may or may not assess you on the algebra of it, but you'll definitely need that algebra proficiency when you're in calculus. Because you know what the hardest part of calculus is? It's the algebra. The algebra is definitely the hardest part of calculus. I mean, calculus is hard on its own, kind of. Like, it's got some crazy fun ideas in it, but the algebra just gets like, well, it's a little much sometimes. All right, so we have this other function. F of x equals 5 minus x over 3x plus 2. All right, let's find the inverse of that one first. So I'm going to write down some steps for finding the inverse. Oh my goodness. I'm going to say them out loud while I write them so you can write them down too. So the first step is to make sure the function has an inverse. So you want to do the horizontal line test. So 1, make sure the function has an inverse. So steps. Make sure it has an inverse function. Right, and this is your horizontal line test. So if we look at this, we know the graph of this square root of 2x minus 3, right, it's going to start at, well, we can look at it, but the graph looks like this, right? This will start here, go, right? Any horizontal line will hit once and only once. We're good. So, yes, it has an inverse function. Now what we're going to do is we're going to replace, and this is just to make it easier to solve, f of x with y. So we're going to take this f of x, and instead of f of x, we're going to write y equals square root of 2x minus 3. Why? Because y is nicer to work with than f of x. Next, what we're going to do is we're going to interchange the roles of x and y. We're going to swap the x's and y's because basically this is like the algebra version of reflecting over y equals x. The a comma b's now become b comma a's. X comma y becomes y comma x. So I'm going to do a little switcherooski here and get x equals square root 2y minus 3. And lastly, we're going to solve for y. Oh, sorry, this isn't quite last. We're going to solve for y in that. And then we will replace y with f inverse of x. And then the last thing you can do is you can verify f of f inverse of x equals x, or f inverse of f of x equals x. All right, so let's go ahead and solve